Okay, we're continuing with chapter 1 in the geometry textbook. In this video, we're going to go through section 1.2, informal geometry and measurement. In geometry, the terms point, line, and plane are described but not defined. Other concepts that are accepted intuitively but never defined include the straightness of a line, the flatness of a plane, the notion that a point on a line lies between two other points on the line, and the notion that a point lies in the interior or exterior of an angle. Some of the terms found in this section are formally defined in later sections of chapter 1. The following are descriptions of some of the undefined terms. All right, so there's going to be terms that they're not ever going to officially define in this course. Some they will, though, but so it says the terms point, line, and plane are described but not defined. They're just accepted intuitively. Like the idea of the straightness of a line. You know, you could come up with an official definition for what it means for a line to be straight. But we're not going to go through that. Official in the sense of, you know, using the deductive reasoning to make using inductive reasoning to do some investigation, and then using deductive reasoning to officially make a formal statement about the straightness of a line. Well, we'll talk about in an upcoming section what makes a good definition, but a quality definition is going to involve the reasoning processes. So, but we're never going to define, make an official statement about what the straightness of a line is. We're just going to accept this into make an informal description of what straightness means and accept it intuitively. Same with the flatness of a plane. Same with the notion that a point on a line lies between two other points on the line. So you have you can think about we'll talk about in a second, the endpoints of a line. And so any point other than the endpoints on a line is going to lie between two other points on the line. Okay, and then the notion that a point lies in the interior or exterior of an angle. So this statement we can come back to later to understand what this means. We need to really understand the meaning of an angle. But some of the terms found in this section are going to be formally defined later. Okay, but now we're going to go over some descriptions of some of the terms that we don't officially define in geometry. Okay, a point, which is represented by a dot, has a location but not a size. That is, a point has no dimensions. An uppercase italic letter is used to name a point. Figure 1.8 shows point A, B, and C. Okay? Yeah, so it's just a point is a location in space. It's the way to think about a point is it's zero dimensional. A line is, for example, is like one dimensional. And why is a point zero dimensional? Because by definition, it has no size. Even though you can put a dot, I guess the dot has a size, but technically a point has no size. It just represents a location in space. So it's zero dimensional. Okay, now the second geometric term that we're never going to officially define is a line. A line is an infinite set of points. I mean, so is a plane, but it's just it's one type of infinite set of points is a line. You know, even 3D space you can look at as an infinite set of points. Points with coordinates x, y, and z, just general 3D space, that's an infinite set of points. So, but a line is one case of an infinite set of points. Given any 2 points on a line, there is always a point that lies between them on that line. So yeah, what they're saying there is that the idea, it's kind of like in algebra, we talk about the number line. Okay, so 0, and I'm going to put 1 here. Between 0 and 1, there's an infinite number of values, technically. You know, you could do 0.000 with a trillion zeros, 523. That's on the number line. So there's always, when it comes to a line, there's truly an infinite number of points. And another way of looking at that is you can take any 2 points on the line, no matter how close they are. You can make them as close as you can think. But then even then, there's going to be a point between those 2 points, except for the endpoints. If you can define a line with, well, no, okay. Actually, technically, a line doesn't have endpoints. A line, you put arrows. So a line extends infinitely in both directions. So there is you could just make the statement that on a line, you pick any 2 points. There's going to be points that lie between those two, at least one point that lies between those 2 points. That's just generally true for a line because a line has no endpoints. But you can still put on a line, you can put like a point here to call it line AB. But it still has no endpoints. But what I drew earlier was a line segment, so a line segment has endpoints, line segment AB, and in this case, yes, the endpoints, if you pick any 2 points on the line, there's going to be a point in between those points because you're going to have to say, you could say maybe I could say point A, and then if I'm going to choose another point, it's going to have to be somewhere on the line. So actually, even for a line segment, if you pick any 2 points, there's going to be at least 1 point between those 2 points, no matter what. So even that's true for a line segment, even if you pick an endpoint, because I could say point A, and then I have to pick another point in here, and that means, and no matter how close I pick a point to the endpoint A, at a second point, there's going to be a point in between those points. I could pick point A and then a point that's 0.000 1 trillion zeros 1 millimeter from point A. Technically, there's a 2 trillion zeros 1 millimeter from point A. So that's in between the 2 points I picked. So, okay, lines have a quality of straightness that is not defined but assumed. Given several points on a line, those points form a straight path. Whereas a point has no dimensions, a line is one-dimensional. Yeah, okay, well, so yeah, the straightness, right? The idea, what they're saying is they're not giving a formal definition of straightness, but I think we all have a sense of what straightness means, and so a line is the definition of a line, it's perfectly straight. And you can think about, you can use your intuition to come up with your own mental definition of what that would mean. And when you learn about machining processes, like in machine shops, one of the specifications is you can specify a flatness of a plane on like a piece of metal or something. They have to make it a certain level, a certain degree of flatness, and you can think about how that's defined. How do they measure the flatness and define and make something flat? It's not possible to make something perfectly flat. That's literally impossible, but a plane is perfectly flat. And I think when you think about flatness, it's this similar idea to what straightness would mean. You would take measurements and you would have a reference plane that's a theoretical reference plane that's perfectly flat. And then so the idea would be you would take height measurements with they've got laser measurement devices that can measure dimensions extremely precisely. And if you took a heightness measurement at a large number of points on the surface of the piece of metal, they would all ideally have the exact same height. But in reality, they're going to differ by, the heights are going to differ by certain micrometers. Visually, it's going to look perfectly flat, but if you look at it from like a micrometer standpoint, you can see what the degree of the actual flatness is. Okay. Now, whereas a point has no dimensions, a line is one-dimensional. That is, the distance between any 2 points on a given line can be measured. Yeah, it has a size. A point doesn't have a size. You can't say with a point, oh, well, come and measure how many fractions of a millimeter is this point. That doesn't make sense. That's technically, this point has no size. This point has no size. A line, though, does have a size. You can go measure a distance between 2 points on a line, and all you need is one dimension. Whereas on a plane, you can't, you can describe the location of a point in the plane with 2 dimensions. Okay, line AB represented symbolically as, so they're doing this, extends infinitely far in opposite directions, as suggested by the arrows on the line. A line may also be represented by a single lowercase letter. Figures 1.9a and b show the lines A, B, and M. Here's, okay, point A, B, and C. Here's line AB. And then here's line M, just lowercase m. When a lowercase letter is used to name a line, the line symbol is omitted. That is, you just say line M. You don't put any line symbol. So if they're saying A, B, and M are the same line, so you could, this is a true statement. Note the position of point X on line AB in figure 1.9c. There's point X. When 3 points such as A, X, and B are on the same line, they are said to be collinear. Okay, so A, B, and X are collinear. They lie on the same line. And really any same line. It's not like they have to lie on these points that are collinear have to lie on a specific line. If you can construct any line that goes through the same set of points, then all of those points are said to be collinear. In the order shown, which is symbolized A-X-B or B-X-A, point X is said to be between A and B. When a drawing is not provided, the notation A-B-C means that these points are collinear, with B between A and C. When a drawing is provided, we assume that all points in the drawing that appear to be collinear are collinear, unless otherwise stated. So yeah, if you just saw a drawing like this, then this is implying visually that these 3 points are collinear. They don't have to make some official math statement. This implies collinear. And you could write this as A, and you want to, or C, B, A, just indicating that B is between C and A. However, in figure 1.8, these points are not collinear. There's no way you can construct a line that passes through all 3 of these points. One line. All right, at this time, we formally introduce some terms that will be formally defined later. Okay, so yeah, now we're going to look at, that was descriptions of terms that we're never going to officially define in this course. Now we're going to look at terms that we're not going to officially define in this section, but we'll define later. So, all right, you've probably encountered the terms angle, triangle, and rectangle many times. An example of each is shown in figure 1.10. So here's an angle, here's a triangle, and here's a rectangle. And in trigonometry, we talked about the official definition of an angle, and we're going to go through that in geometry as well. You have a sense of what an angle is. I think, as you grow up, you have a sense of you're familiar with what an angle is, but what's the official way you would define that? How would you officially make an official definition for what an angle is? I think triangle is pretty intuitive. It's a 3-sided figure, but I mean, you could still come up with a more official definition for it. But an angle is a little bit trickier to think about. What exactly is an angle? Using symbols, we refer to figures 1.10 A, B, and C as, so angle ABC, triangle DEF, and rectangle WXYZ. Okay? So symbolically, you can say angle ABC. Here you can say triangle DEF. Here you can say rectangle WXYZ. You just don't want to skip over a point. You could say rectangle YXWZ, rectangle ZWXY, but you don't want to say rectangle WYZX. Same with the triangle. You don't want to skip over a point, and same with the angle. Because this is going to, putting the B in the middle is going to indicate that B is the vertex of the angle. Some caution must be used in naming figures. Although the angle in figure 1.10a is called angle CBA, it is incorrect to describe the angle as angle ACB because that order implies a path from point A to point C to point B. And exactly, you got the order. You don't want to skip. You don't want to skip in terms of skip a letter in terms of if you were drawing the triangle, the rectangle, or the figure. That's the idea. Think about if you were drawing it. You want someone needs to be able to this rectangle draw it, and if you put a rectangle ZX, well, draw it without picking up their pen off the page. Think about it that way. And so if you put rectangle ZXWY, well, how could you draw that without picking up your pen off the page? Same with the triangle and the angle. Okay, the point B at which the sides are meet is called the vertex of the angle. That's where the two sides of the angle meet. So an angle is we're going to officially define an angle later, but just to give you a preview, the key features, you might think, well, you have to have a circle to define an angle. That's not true. An angle, to define an angle, you need two straight sides. Okay, straight sides. The sides need to be straight lines. Well, not lines, you could have, it doesn't have to be a technical line. It can be line segments, rays, an actual line, whatever, but two straight sides. And then those sides are going to meet at a common point and that's called the vertex. And then those lines are going to be rotated with respect to one another about the vertex. And the degree of opening between the two straight sides based on the amount they've been rotated relative to one another, that's the angle. So again, it's straight sides with those sides meeting at a common point called the vertex of the angle. And then there's a separation between the straight sides that's based on a rotation of the sides relative to one another about that vertex point. It's like if it was hinged at the vertex point. And so in that amount of opening is an angle. So the key terms here that come into play with defining an angle are straight sides, and not just straight sides, but two straight sides, common point that the straight sides meet called the vertex, and then rotation, specifically about the vertex, rotation. That's why when you're drawing an angle, like what I just did, you don't do it straight like that. It's always a curve because there's a rotation involved. Okay, and again, the order is important because of the naming convention, because you want to that lets you see exactly what the vertex is. Okay, now you can also write an angle as just angle and put the vertex. So instead of angle ABC, we could have called that angle B. You could just represent an angle by just its vertex letter. Or angle 1, you can number angles and call I could say this is angle 2. You could do that. Or angle A, or angle lowercase c. You could just name it by its vertex. All right. Now, the points D, E, and F at which the sides of triangle DEF, which you could name it any way you want, just the order needs to be correct, meet are called, those are vertices. So that's plural of vertex. It's the vertices of you don't call it a vertex on a triangle or a rectangle or polygon. You call those vertices, which is plural of vertex. Similarly, W, X, Y, and Z are the vertices of the rectangle. The vertices are named in the order that traces the rectangle. A line segment is part of a line. So yeah, it's a portion of a line. It consists of two distinct points on the line and all points between them. Using symbols, we indicate the line segment by, and so instead of line BC, you just leave off the arrows. That's line segment BC. Note that segment BC is a set of points but is not a number. So yeah, what they mean here is that, okay, if you think about it, if you said, if you specified a line, so line M, or what was it, line AB, this can never be a number because there's no length of a line. It's because it extends infinitely in any direction. However, a segment can be associated with a number. What they're saying here is, from a notation standpoint, this isn't a number. And the notation they're referring to here is you would leave off this line at the top, and that would indicate the length of the segment. But there's different notations I've seen. You could say like the magnitude of segment BC, and that would be that's a number. That's a length. And like with an angle, you have angle C. I guess that's just specifying the angle, but you could say like the measure of angle C, and so an angle is associated with a number. A segment you can associate with a number. It has a length, a line segment. But there's some things, there's no, like a triangle ABC, that's not a number, right? You have to give more, I mean, there's numbers associated with triangles, maybe the area of a triangle, but you have to specify area. So, but the notation they're saying here is that if you wanted to indicate the length of line segment BC, you would leave off the line at the top. But there's different notations that you'll see. We're not going to get into too much depth on official notation here. Again, this is not for math majors. So, but yeah, BC without the line it's saying at the top is a number. And note that the sides of a triangle or rectangle are line segments. So yeah, the sides of a polygon, like a triangle or a rectangle, those are line segments, right? You can say that this is line segment DE. You could line segment DE. And what is the length of that line segment? What's the magnitude of it? Okay, measuring line segments. The instrument used to measure a line segment is a scaled straight edge, such as a ruler, a yardstick, or a meter stick. So yeah, there's going to be a whole separate playlist on units and measurement. So if you're looking to understand the fundamental basic ideas around measurements in units, unit systems, the metric system, the English system, and different ways, different quantities that we measure, you're going to get the full scope of that in the units and measurement playlist, it's not, at the moment, it's not posted, but it will be. All right, but when it comes to a line, the length of a line, the length of a line segment, we use a straight edge that's been scaled. So it's not just a straight edge, but a straight edge that has a scale on it, like a scale here. These distances in space between these tick marks is based on a standard that is universally accepted throughout the world. And so back in ancient times, it would be a foot was approximately the length of someone's foot, or the king's foot. That was the standard. But now it's more precise than that. It's based on the speed of light. And what you can think about, though, is, so you might be saying, oh, so this was calibrated using a ruler like this, using the speed of light. Well, no, that's if you need something that measures to that extreme of a precision, then you're going to use an expensive instrument. But what you can think about is, they've got this very expensive way of reproducing this length that's based on the speed of light that's equal to a meter. And so then wherever this is in France or something, so then people come in with expensive equipment and calibrate like 10 other pieces, but then some accuracy is lost whenever they do that calibration. And then those pieces are sent out around the world, and then, kind of indirectly from there, plants that manufacture rulers and tape measures and stuff they're going to receive something that's been calibrated maybe, it's like fourth or fifth in line from actually being calibrated from the master system. And it doesn't matter because these don't need a ruler, a tape measure don't need that level of accuracy for construction work and whatnot, and for just, for doing sketches on a page. Okay, but to measure distances, and when you say that, most of the time you're talking about a straight line distance. I mean, you can think about an arc, a distance of an arc, but right now we're talking about a straight line distance, which is the distance of a line segment. You use a straight edge that has a scale on it, like a ruler or a tape measure, or even a protractors will have a straight edge at one end and there'll be a scale on it. Okay, so they talk about some of the details of taking measurements. I think we all know how to measure something with a ruler, but as far as if you getting into the specifics of that, go check out the units and measurement playlist if you want to get in more detail on that. But we all know how to measure something with a ruler, the length of a line with a ruler. Okay, in example 2, a ruler not drawn to scale is shown in figure 1.13. In the drawing, the distance between the connective marks on the ruler corresponds to 1 inch. The measure of a line segment is known as a linear measure. All right, so let's see. In rectangle A, B, C, D of this figure, the line segments AC and AD shown are the diagonals of the rectangle. How do the lengths of the diagonals compare? So this is a rectangle, so we would expect, just my intuition tells me that the diagonals are going to have the same length. And so if each of these tick marks is 1 inch, you can count there's 10 inches, and so we would expect, my intuition would tell me that this segment would be 10 inches, and they say that is the case if you measured it, if you turn the ruler and measured it. And that measuring process, that is what? That's inductive reasoning. And so my intuition told me that that the diagonals are equal because of the symmetry of the diagonals of rectangles, I would assume. Then you do inductive reasoning and actually take measurements of both diagonals with the ruler, see that they're according to your measurements they're equal. Then you make an official statement saying the lengths of the diagonal of a rectangle are equal because of, here's the evidence. Now, to me, that wouldn't be that wouldn't be an official proof to say the diagonals of any rectangle are going to be equal in length because I drew a rectangle and I measured the sides and made sure that the two of the side lengths were equal in length and the other 2 of the side lengths were also equal in length, but all 4 don't have to be equal in length. I drew the diagonals, I measured, and I saw that the diagonals had the same length, so that means that every single rectangle, the diagonals are going to be of equal length. To me, that's not a good enough proof that any rectangle, no matter what the size of it, the diagonals are going to be equal length just because you measured the diagonals of one particular rectangle and found that they were equal length. Well, what if you draw a rectangle of a different size? There's an infinite number of different sized rectangles. How can you state for sure that the diagonals of any rectangle are going to have equal length? And so that's the way we're going to go through the proofs of different properties in this course. Okay, in figure 1.14, point B lies between A and C on line segment AC. If AB is equal to AC, then B is the midpoint of segment AC. When AB is equal to BC, the geometric figures segment AB and BC are said to be congruent. In effect, geometric figures are congruent when one can be placed over the other in a perfect match. Numerical lengths may be equal, but the actual line segments, geometric figures, are congruent. The symbol for congruence is this. So equal sign with there's congruent. Thus, segment AB is congruent to segment BC if B is the midpoint of AC. Example 3 emphasizes the relationship between segment AB, BC, and AC when B lies between A and C. Okay, so we've got segment AC here, and then they put a point in between A and C. If that point is located so that the length of AB is equal to the length of BC, then you say that B is the midpoint of segment AC, okay? Now, furthermore, if you're referring to, so they're referring to the length of AB is equal to the length of BC here. But now the next sentence, they're talking about a comparison, not between the length of AB and BC, but between the actual geometric figures AB and BC, right? Because that's what they're trying to note, that segment AB with the segment with the line on top and segment BC, those aren't numbers. They're saying those are figures. Okay, so we know that the length of AB is equal to the length of BC, the line segments, So what does that mean about the figures, the comparison between the figures? Because remember, we can't say that this doesn't make sense. Because when you have an equality, you're talking about numbers. So when it comes to, if you have two line segments that are equal in length, then the actual geometric figures there are said to be congruent. And what does that mean? The way you think about two geometric figures, whether it be a triangle, a rectangle, a trapezoid, whatever, the two geometric figures are congruent is if you can lay them on top of one another and get a perfect match. Then they're congruent. So does that mean they're equal in length? But no, we're not referring to a geometric figure as a number when we talk about congruence. When it comes to congruence, we're not referring to numbers, we're referring to shapes. And so, okay, let's say I took AB and I drew it like this. There's AB. And then let's say I took BC and I drew it like this. Are those two congruent in this case? Can you say that that segment AB is congruent to segment BC, the shapes? Yeah, it doesn't matter how they're oriented. The idea is the key. This is really important. The key is that you can take any shape and you can flip it out of the page. You could flip it horizontally, vertically, in or out of the page, rotate it, do whatever you want. You just can't scale the size of it. You can't scale it up or down. You can't change the shape at all. But you can move it. You can move it in 3D space however you want. And if doing that, you can take two shapes, whether they be lines, triangles, whatever, and lay them on top of one another, and they line up perfectly. Then you say they're congruent. That's what congruence means. Okay, and then again, you cannot say two shapes are just equal. You have to say congruent, because when you say equal, you're implying numbers. The length of segment AB and the length of segment BC are equal, but you can't say the shape, the line itself, and of AB and the line BC itself are equal. What's equal? We say congruent, and we use this symbol. Okay, so yeah, that's really important that you understand exactly what congruence means. Of the shapes being congruent. We're going to see you might have triangles that it's hard to notice if they're congruent or not. But remember, you can flip this horizontally, vertically. You can kind of rotate it into and out of the page. You can do whatever you want to the two shapes, other than actually scaling them up or down. Like, you can't take this shape and then scale it down to a smaller size. You can't change the size of it at all, but you can change the orientation in any way you want of both shapes. And by doing that, if you can lay them on top of one another and it's a perfect match, then those shapes are congruent. Okay. In figure 1.15, the lengths of segment AB and BC are AB is equal to 4, BC is equal to 8. What is AC, the length of AC? Oh, okay. So a new figure here. AB is equal to 4, BC is equal to 8. So what is the length of AC? Well, that's going to be the length of AB plus the length of BC. So according to this notation, we would write that as AC, with no bar on top, is equal to AB plus BC. Okay. Now, let's just think about this for a second. Could you say that segment AC is equal to or is congruent to segment AB plus segment BC? Well, no, because that's too ambiguous. That's I guess kind of you could say that, but the issue is that what does this mean? This, when you have a plus here, that's a operation between numbers. A plus, you're adding numbers. We defined addition and subtraction back in elementary school. But what does this mean as far as you're adding two shapes? I mean, I could take segment AB right? And I could add it to BC and put it here. Well, is that congruent to this? Well, that wouldn't be the best comparison. So, okay, because these are different. So I could take, here's AB, and here's BC, but I could add them together. I could do this. Okay, is ABC here congruent? Is this shape congruent to this shape? Well, no, I can't. I can't reorient these in any way I want and lay them on top of one another, and it's a perfect match. So the issue with this statement is what does this mean in terms of shapes? This plus. What is the definition of plus in terms of shapes? So no, you can't say this. Okay, we'll finish this section in the next video.